Good morning, everyone. So, today we are going to start a new chapter, chapter 14. Name of the chapter is Principle of Mathematical Induction. Okay, in short, we can say PMI. Okay, so in this chapter, we will learn like how to prove a given statement is true for all natural numbers. Okay, like here you can see for the exercise 14, question number 8. Here you can see that one statement is given to you that 1 plus 2 plus 3 plus dash 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 plus n will be equal to n in bracket n plus 1 upon 2. Okay, that means if I take like this 1 plus 2 plus 3, then using this statement this should be equal to 3 plus 1 upon 2. Okay, so 3 into 4 by this, so this should be equal to 6, and you can see yes, it is 6. So in this chapter we shall just prove that the statement involving n, where n belongs to natural number, will be true for all the natural numbers. Okay, so for that we have to follow this procedure. Like here it's written, you can see here it's written that let Pn be a statement involving the natural number n. So here this statement, okay, will be denoted as Pn. Why? Because this involves natural number. Clear? So the given statement will be denoted by this Pn, where n is the natural number. And next what we will do is we will check whether the given statement is true for n equal to 1 or not. Okay, then second is we have to assume that the given statement is true for n equal to k. Okay, and thereafter we have to show that the statement will be true for k plus 1. Okay, so that means statement is given to you. First thing that you will do is you will see whether that is true for n equal to 1 or not. If it is true, then second work will be to assume that the statement is true for n equal to k, and thirdly you have to show that the statement is going to be true for k plus 1 also. Okay, so once we do the question, things will be more clear to you. Okay, so let us do this question 8.1. Okay, so principle of mathematical induction, in short PMI. So let us do this question number 8.1. Okay, okay, so question number 8.1. so solution. So this is the statement given to you. So what you will do, first thing you will write let Pn, you will write colon, and then you will just copy the statement. So 1 plus 2 plus 3 plus dot 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 plus n is equal to n times in bracket n plus 1 whole divided by 2. Okay, so first thing you should do this. Okay, now we should show that this statement is true for n equal to 1. So we'll write for n equal to 1, left hand side is equal to, so we have to find left hand side separately and right hand side separately. So here you can see that left hand side is following this pattern 1 plus 2 plus 3 till n, but here our n is what? 1. That means we have to just write the first one only. Yes, done. So left hand side is coming 1, and right hand side will be given by n in bracket n plus 1 upon 2. So here my n is what? 1. So we'll get 1 plus 1 upon this, so you are getting 1. So here what do we observe? Therefore LHS is equal to RHS. Okay, so since we got LHS equal to RHS for n equal to 1, hence this P1 is true. Okay, P1 is true. Done. So as we had seen over here, that first thing we have to show that P1 is true. Okay, and then we have to assume that Pk is true, and then using this assumption we have to show that Pk plus 1 is true. So first part is done. Now second will be, let, one second. So now we can write, now let Pk be true. Then now since I'm saying that Pk is true, so it means that if you replace n by k, okay, on both the side, then the statement will be true. Okay, so once I have written Pk is true, then we have to write like this. We have to write the same thing. The only thing is that we have to replace that n by k. So we will write 1 plus 2 plus 3 plus dot 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 plus k is equal to k times in bracket k plus 1 divided by 2. Okay, you can give this as equation 1. Okay, so this is the assumption, okay, that Pk is true. Now using this assumption we have to show that Pk plus 1 is true. Now what we'll do is, now we'll write 1 plus 2 plus 3 plus dash 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 plus k. Okay, we have to show for k plus 1. Okay, so firstly we will write till k, and then we will write for k plus 1. So k plus 1. Done. Now this will be equal to, now you can see that this part on the left hand side, this part on the left hand side from equation 1, okay, this is equal to k plus 1 upon 2. So you will write k this and plus this one. Okay, actually what we are trying to bring on the right hand side is, like here it is from 1 plus 1 to k plus 1, so we are trying to bring this now. Following the same pattern, no? Okay, like here the last term is k. Okay, so on the right hand side it is k plus 1 upon 2. So here in this case last term is k plus 1. So on the right hand side I want to bring this k plus 1, okay, and in bracket k plus 1 by 2 using same pattern. Okay, so if we could show that, therefore this statement will be true for every natural number. Okay, so now see, I can take LCM. In the numerator you will have k plus 1 common, so take this out. You are left with k plus 2 upon this. Now further k plus 1, and this k plus 2 can be written as k plus 1 plus 1. Okay, now can you see this, you have got that. Okay, let me write. This implies that 1 plus 2 plus 3 plus dash 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 k plus 1. Can you see this is equal to this, and it is coming in this pattern: 1 plus 2 plus 3 plus dash 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 plus n is equal to n plus 1 by this. Last term is n, so here n plus 1. So same pattern is followed over here. Yes or no? The last term is k plus 1. Okay, last term is k plus 1. So here you got k plus 1, then k plus 1 upon 2. Okay, so that means this is, that means we got this statement. Yes, plus was missing there. Yes, so we got this statement. Therefore is true whenever is true. So due to our assumption, we were able to show that this statement pk plus 1 is also true. Okay, so therefore this is true. Hence the statement Pn, okay, is true for every natural number. Okay, so we have proved using mathematical induction. Okay, okay, next question, question 8.2. Okay, this is the statement, and using principle of mathematical induction, we have to show that this is true for every natural number. So solution, first thing, let Pn 1 square plus 2 square plus 3 square plus dash 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 plus n square is equal to n plus 1 in bracket, then 2n plus 1 in bracket upon 6. Okay, so we have to show that this statement is true for every natural number. Okay, so firstly we have to show that this statement is true for n equal to 1. For n equal to 1, your left hand side will be 1 square, that is 1, and your right hand side will be 1, it will be 1 plus 1, 2 into 1 plus 1 upon 6. So you get 2 into 3 upon 6, that is 1. Yes, so therefore your left hand side is equal to right hand side. Hence, or you can say thus P1 is true. Once you have shown that P1 is true, then you have to assume that Pk is true. Okay, and using that we have to show that Pk plus 1 is true. Okay, now let Pk be true. So when you say pk is true, that means what? For the given statement, no, whatever statement is there, you simply replace n by k. Okay, so you'll get 1 square plus 2 square plus 3 square plus dash 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 plus k square is equal to k plus 1 2k plus 1 upon 6. Give this as equation 1. Okay, so this is our assumption. Now using this assumption, one second. Okay, so using this assumption, we have to show now that if I write like this, if I write for k plus 1 also, then this should follow the same pattern, and on the right you should get this. So using this assumption, we should be able to show that this, okay, will be equal to this. That means this pk plus 1 will be true. Why I'm saying pk plus 1 true? Because from this much is pk, okay, and here I'm adding next number, okay, that is k plus 1. So if this one holds, okay, according to this pattern only, then we say that pk plus 1 is true. Okay, so whenever you are trying to show that pk plus 1 is true, so you should remember that like what will happen wherever is k on the right, no, okay, that k will be replaced by k plus 1, okay, and that is what we are looking for on the right hand side. So let us see. So now 1 square plus 2 square plus 3 square plus dash 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 plus k square plus k plus 1 square is equal to. So you have to write this much, and then you can see that this from 1, okay, this one from 1 is equal to k plus 1 2k plus 1 upon 6. So you'll write k plus 1 2k plus 1 upon 6 plus k plus 1 whole square. Okay, now you have to try to make this one, okay, you have to try to make this one this k plus 1 k plus 1 plus 1 2k plus 1 plus 1 upon 6. Okay, means if you replace k by k plus 1, so whatever you get, that should be coming here, okay, at the end. So let's see. So take LCM. So you get k plus 1 2k plus 1 plus 6 times k plus 1 whole square upon 6. You can see in the numerator k plus 1 is common, so you can take this out and you are left with k 2k plus 1 plus 6 times k plus 1, and in the denominator you are getting 6. Then k plus 1 open the bracket, you get 2k square plus k plus 6k plus 6. Now k plus 1, 2k square plus 7k plus 6. You can see here this is a quadratic expression, so I can factorize it. So k plus 1, and this one becomes 2k square plus 4k plus 3k plus 6. Then k plus 1, 2k, k plus 2 plus 3, k plus 2 upon 6. Then k plus 1, 2k plus 3, and here k plus 2. Then this becomes k plus 1, and this can be written as 2k plus 2 plus 1, and this can be written as k plus 1 plus 1, k plus 1. Here 2 is common, okay, for these two terms. So 2k plus 1 plus 1, and here k plus 1 plus 1 upon 6. Now you can rewrite it as this. Okay, so this implies that we got 1 square plus 2 square plus 3 square plus dash 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 plus k square plus k plus 1 whole square is equal to this. But you can observe that this is nothing but this is statement, this one, okay, because here you can see last term is what, k plus 1. So here you are getting k plus 1 into k plus 1 plus 1 into 2 times k plus 1 plus 1. Yes, because the given statement was like this: 1 square plus 2 square plus 3 square plus dash 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 plus n square is equal to n plus 1 2n plus 1 upon 6. Yes, the last term was n, so here we got n, then n plus 1, then 2n plus 1. Here you can see last term is k plus 1, so here we are getting k plus 1. Okay, you can see this k plus 1, then k plus 1. Okay, because if you think that this is like z, okay, think that this is like z, then this whole thing will be z, z plus 1, and then 2z plus 1. Yes or no? So you can see that the same pattern is followed for k plus 1 also. Okay, so therefore this whole thing that you have got is nothing but the statement p k plus 1. Yes, so this implies p k plus 1, 1 square plus 2 square plus 3 square plus dash 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 plus k square plus k plus 1 whole square is equal to k plus 1. Then you can write, if you want, k plus 1 plus 1, then again 2 times k plus 1 plus 1 upon 6. Okay, therefore pk plus 1 is true for true whenever, okay, whenever pk is true. Clear? Hence the given statement Pn is, or you can write hence by principle of mathematical induction, Pn is true for all n belongings to natural number. Okay, so this is done. Now let us see question number 3. Question 8, sub question 3. So using principle of mathematical induction, we have to show that this statement is true. So solution, let Pn, means we are considering this statement as Pn. So 1 cube plus 2 cube plus 3 cube plus dash 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 plus n cube is equal to n plus 1 upon 2. Done. Now we have to show that this is true for n equal to 1. So we'll write for n equal to 1, left hand side will be 1 cube, that is 1, and right hand side will be 1 plus 1 upon 2 whole square. So you get 2 upon 2 whole square is equal to 1. Okay, therefore LHS is equal to RHS. Thus P1 is true. So first part is done. Now what we have to do? We have to assume that pk is true. Okay, so we'll write, now let pk be true. When I say pk is true, that means whatever statement you have been given, you have to write the same thing, but wherever is n, that has to be replaced by k. So I get 1 cube plus 2 cube plus 3 cube plus dash 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 plus k cube is equal to k in bracket k plus 1 whole divided by 2 whole square. Okay, you can give this as equation 1. Now your job is to show that this state that pk plus 1 is also true. Okay, so let's see now. Now you'll copy till here. Okay, you'll copy till here, and then you will add the next term. So next term k plus 1, you can see for each term we are taking cube, so we have to take cube. Okay, so we'll write 1 cube plus 2 cube plus 3 cube plus dash 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 plus k cube plus k plus 1 cube. Okay, so you have to write this, and at the end, okay, at the end you should be able to get using this same pattern, like here you see that what we had in the statement 1 cube plus 2 cube plus 3 cube plus dot dot dash plus n cube. So on the right hand side we had this. Yes, we had this. So here you have taken till k plus 1. So at the end, no, at the end on your right hand side you should have this k plus 1, k plus 1 plus 1, okay, whole divided by 2 whole square. Clear? Like here in the statement, when last term is n, okay, then you have n plus 1 upon 2 whole square. So same way here our last term is k plus 1, so we should have k plus 1, like here n, then n plus 1, last term is n, so n plus 1. So here last term is k plus 1, so we should have k plus 1 upon 2 whole square. So in this at the end, okay, by simplification, okay, you should be able to show this, okay, you should get this on the right, then only you can say that pk plus 1 is true. Okay, so how we are going to show that? For that we have to use 1, okay, and after that simple calculation will help you. Okay, so see over here, so for this much, okay, on the right I can write k plus 1 upon 2 whole square, then k plus 1 whole whole cube. Done. Then this square is for k and for k plus 1 as well as for 2. So I can write k square k plus 1 whole square upon 2 square. And this k plus 1 cube can be written as k plus 1 whole square and k plus 1. Take LCM. So here 2 square will be 4. So you get k square k plus 1 whole square plus 4 times k plus 1 whole square k plus 1, and here in denominator you have 4. Now in the numerator you can see that k plus 1 is common, k plus 1 whole square is common. So we can write k plus 1 whole square, then you are left with k square plus 4 times this. K plus 1 whole square, and here you get k square plus 4k plus 4 upon 4, then k plus 1 whole square k square, this 4k can be written as 2 times k into 2, and this 4 can be written as 2 square. Then k plus 1 whole square, and this you can see this can be written as k plus 2 whole square. Next you get k plus 1 square k plus 1 plus 1 whole square, and here 2 square, and this whole thing can be written as k plus 1 and then k plus 1 plus 1 upon 2 whole square. Yes, so I was telling you that the given statement is like this: 1 cube 2 cube plus 3 cube plus dash plus n cube is equal to n plus 1 upon 2 whole square. Yes, so I told you that in order to show that pk plus 1 is true, you should be able to show this. You should be able to show this. Like here it had ended at n, so we got n plus 1 by 2. So For k plus 1, if it is ending at k plus 1, then you should be able to show k plus 1, k plus 1 plus 1 upon 2 whole square. So see, we were able to show this, yes or no? So therefore we can say that the statement pk plus 1 is true. Okay, so here I can write now, this implies 1 cube plus 2 cube plus 3 cube plus dash 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 plus k cube plus k plus 1 cube is equal to this, and this implies that this is pk plus 1 statement. Okay, so now we can write, therefore pk plus 1 is true whenever pk is true. Hence, by PMI, in short, principle of mathematical induction, Pn is true for all n belongings to natural number. Okay, so this is all for today's class.